I am pleased to introduce our next speaker, Dr. Nele Famaey. Dr. Nele Famaey is a researcher that focuses on the biomechanics of growth and remodeling phenomena in the cardiovascular system, the brain, and the cartilage. She holds a PhD from the University of KU Leuven in mechanical engineering, and she is currently an associate professor in the mechanical engineering department in the biomechanics section. There, she leads the soft tissue biomechanics group that focuses on providing support for clinical decision-making and medical device design through in silico modeling.
Okay, thank you very much for the introduction, and thank you for having me here. When I was packing my bag yesterday, I really didn't know what to put in. A sweater or no sweater, long pants, skirts, raincoat. I had no idea. To make that decision, I have to base myself on physical reality, the weather, with the weather that it was going to be today, but of course I didn't know yet. Luckily, there are meteorologists, and they take measurements of the weather, they take temperature measurements, they measure the wind speeds, etc. I don't know everything they do, but they use all these measurements to build up mathematical models, and then they implement those models in a computational system. And then I can check on the Google Weather app and get like a small version of that computational model, and based on that, I can make my decision and, well, see what to wear. But, well, to be on the safe side, I brought my sweater and my raincoat anyway, because, well, when they measure the temperature, when they do all these measurements, there is a lot of measurement uncertainty. A lot of modeling assumptions are made when the mathematical weather models are built, and obviously when you have to then implement your nice analytical models into a computational system, other discretization errors are made, and finally, calibration errors are made when the measurements are used to calibrate your model. And of course, the Google Weather app just selects a couple of things from this more complex model, and reporting errors, all of that makes that there is a lot of uncertainty in this whole framework, and that's why I brought my extra sweater. And of course, what I'm wearing or what I'm not wearing is not really a matter of life and death, but sometimes decision-making is a matter of life and death. Like here, for example, you can see an ascending thoracic aortic aneurysm, and this is a life-threatening condition because if this aneurysm dissects or ruptures, this can be very often fatal. And right now, when patients have such an aneurysm, what they do is, or actually it's usually just noticed by accident because they have a scan for other reasons, and then they notice this dilatation. And so what is done? The cardiologist measures the maximum diameter of the aneurysm, and based on that, they decide whether or not to operate. So if the diameter of this ascending thoracic aneurysm is higher than a critical value, well, then they take out the diseased part and they replace it with a graft. And on the other hand, if the diameter is not yet reaching that critical value, they wait, and you can go for a follow-up scan, and every 6 months you get a new scan and they check whether you reached it, yes or no. Well, there's a lot of things problematic with this kind of decision-making, because very often the surgeons then operate on the tissue, they resect the diseased aneurysm, but actually they notice, well, the quality of the aneurysm was actually not that bad yet. I shouldn't have operated yet on this patient. And if you consider the fact that there is very high or perioperative mortality, and that the cost of these procedures is also very high, well, you really don't want to be too careful, and you don't want to have these unnecessary surgeries. But on the other hand, well, you don't want to be too late and have this patient do a dissection or an aortic rupture. And here you can see, well, 60% of wall failures occur at diameters below this critical diameter. But of course, there is a bias here because obviously many people are operated before the critical diameter is reached. But still it shows, in general, that there is something wrong with this decision-making process. So if you think of it from an engineering perspective, just having this diameter for all different types of patients, young, old, more corpulent, less corpulent, female, male, it doesn't make sense that they all follow this same diameter criterion. And a bit of, categorization is done, but actually really not all that much. 55 millimeters that's the threshold that cardiac surgeons use. And this really does not correlate with the actual failure risk. And from an engineering perspective or from a mechanics perspective, well, when will the wall rupture? Obviously, when the peak wall stress, or the stress that's currently present, the maximum stress that's currently present in the aneurysm, does it exceed the wall strength, so the maximum stress that the aneurysm can bear? Or if you put it on an axis here, the strength needs to be far enough, still removed from the stress that's currently present in the vessel. So that seems like quite a simple and logical criterion to work with. The problem is there are no direct biomarkers for stress. We can measure the temperature of the patient, we can take a scan, but we can't directly measure the stress inside the patient. And that's when we get all excited, because it means that we can use our in silico models. So that makes us in silico modelers happy. We can try to build finite element models or more simplified semi-analytical models of the aneurysm. And obviously for that we need a lot of information. We need to put information about the geometry of the aneurysm. We need information about the pressure that is currently present inside the aneurysm. And we need some patient-specific material parameters. And when we have all of that, we can make a fancy finite element model, and we can calculate the peak wall stress along different directions, because that's obviously a 3x3 tensor stress. And we can see where the maximum stress occurs inside this aneurysm. On the other hand, we can have some information, infer some information about tissue strength. And then when we compare these, we have our metric, and we can tell the surgeon very proudly, this patient needs operation, this patient does not need operation. But of course, to get all that information, all that patient-specific information, we need to do all kinds of measurements, and these measurements induce a lot of uncertainty. So basically, well, not just the measurements, but the whole framework that I showed, a lot of uncertainty is being induced. So when we replace the actual physical reality by our computational model, we can't work in this deterministic way, because we know that our values will be suffering from quite a lot of uncertainty. And it could be something like this, but it also could be something like this, or it could be even worse. And in the end, we're comparing things that we really shouldn't be comparing anymore, because we have no idea what we're speaking about. First, or before we should go into these kind of models, we need to think about all the sources of the uncertainty and whether or not they can be reduced before we dare to take that information and bring it to the decision maker, in this case, the cardiac surgeon. So in this case, we have our same, well, modeling scheme, and the decision now is not what to wear, but whether or not to operate on a patient. And we have all these errors that can occur during that whole modeling process. And what's more, we're dealing with patients, so we have interpatient and intrapatient variability. And like was said in the previous lecture, there is not a lot of data available. There are just that many patients or patient data sets available. So we also make sampling errors, and all of that needs to propagate into the system. And just to be clear, it's very important that we make a distinction between variability and uncertainty. So on the one hand, we have patients that differ. Everybody is different. Everybody here in the room is different. So if I would take all of your aortas and I would measure the wall thickness of these aortas, I would get different values, and that would be normal. And I would have to know that it's important that I know that each of you are different. So it's physically there, and we cannot minimize that variability. On the other hand, I can take an aorta, I can measure the thickness of that of the wall of this aorta, and if I would do that measurement 3 times, I would get a slightly different value every time. And this is a variability that's physically not there, and that's the one that we should try to minimize. So it's really important when you think of variability that you consider those 2 different kinds of variability. So actual biological variability in our case, and the epistemic uncertainty. So our focus for today is on the input side. What are we feeding into the model quality in is quality out, or what was said before, garbage in is garbage out. We need to think about what we're putting in and the kind of errors that are related to what is going into these models. So the sampling errors, measurement uncertainty, modeling assumptions, calibration errors, but it all seems a bit vague. What is it? So let's try to walk through it and see what that looks like for our specific case of aortic aneurysm decision making. So going over this, let's start with, well, the part that I don't have to say much about because there was a lecture about it in the previous lecture was all about image segmentation and how to do that in a smart way. But I also think that it was clear from the previous lecture that this definitely still induces, there's still a lot of uncertainty. Even when we use machine learning techniques, we will always be dependent on the resolution of the scan, and we will have segmentation errors regardless of the techniques that we use. On the other hand, we need to measure the patient-specific pressure. And in our case, since we want to actually link the deformation during a cardiac cycle with the pressure evolution during the cardiac cycle, we need to synchronize those two data sets. And here we again make synchronization errors. And obviously, when we're measuring the pressure, we're again susceptible to the measurement resolution of something that is usually done in a rather crude way, measuring pressure with a sphygmomanometer. And we usually measure the pressure somewhere in a brachial location, and we have to transform that to the actual pressure close to the aorta. So all kinds of errors are being made here. And what's more, in the case of patient pressure, the patient is, we measure the pressure of the patient when he's in the scanner, or close to when he's in the scanner. But during the day, the pressure of the patient actually varies quite a lot. We always think our pressure is the famous 12/7 or 12/8 is what it should be. But it really depends quite a lot on the time of the day, whether you've just eaten, yes or no, whether you were sleeping, yes or no. So this is also intra-patient variability that we need to propagate through the model. And each of these uncertainties and variabilities come with their distribution. If we take enough measurements, we can figure out how this distribution looks like for each of these variables. But we need to figure out what kind of distribution matches best. So for example, we can take a lot of pressure measurements for a certain patient throughout the day, and then we have to figure out which distribution would be the best one for the pressure of our patient. And we can find, for example, here, that a normal distribution fits quite well, and we can find the standard deviation for the pressure, in this case, the mean arterial pressure of our patient. But when we do that, obviously, we make a modeling assumption. We assume that this specific uncertain or varying parameter can be described by a certain probability distribution function. We're simplifying reality to be able to model it practically in our system. So that's a modeling assumption that we are already making before we even used any model in the first place, well, or the actual computational finite element model. Just already on this side, you already see a big list of uncertainties and variabilities appearing. That's step one. And now let's go through the other input regions, and let's start with what we could say the more simple one, the tests that we need to do to get an idea of the patient-specific tissue strength of the aneurysm. So looking at the variabilities and uncertainties that appear there, we need to think about, well, what's our scientific methodology for getting a hold of those parameters? Well, obviously, we cannot collect in a patient-specific way, in a prospective way, information about the failure data of a patient's aneurysm, because that would defy the purpose of trying not to operate on this person. But we can build up a retrospective database. So that's what we did. So in the university hospital, we started a clinical trial where all patients that were scheduled for aneurysm, for graft repair or graft replacement, we had them enter the clinical trial, and when they received their graft, the diseased tissue was brought to our laboratory. We could analyze it in all kinds of ways, and one of the ways in which we analyzed it was through uniaxial tensile testing, and then if we collect data from enough patients, we can put that into a database. But obviously, since we are then dealing with different samples from the same patient and then different samples from multiple patients, we suffer from all this inter- and intra-patient variability and definitely also from sampling errors. And in this case especially, well, we're only taking data from patients that are already scheduled for surgery, and even though the criterion is not completely representative, it still means that we are only testing patients that are already further away on the spectrum of, weakening of the aortic tissue. So that's one aspect of it. And this is, for example, just what we did. We didn't only use our own uniaxial tensile testing data. This is a topic that's been quite popular for quite a while. And we asked all these groups of people to send us their uniaxial tensile data of all patients that were collected during all those studies. And we pulled them all together so that we could really make this distribution of strengths in the circumferential and in the axial direction of aneurysm tissue. And here you can already appreciate, for example, the difference in distribution of the complete, the interpatient variability, and then just, for example, the variability already just within one patient, just taking samples from different locations along the aortic arch or along the circumference of the aorta. So again, here, once you have those measures, you can try to fit distributions on them and then work with those distributions in your model, but you're again making a modeling assumption there. We are actually still making other modeling assumptions and also dealing with modeling measurement uncertainty. And those are actually the two questions that you should always ask yourself. First of all, well, are we doing the right test? And then, are we doing the test right? So first, the question of are we doing the right test? Well, let's think about a uniaxial tensile test. And this is a graph where you can see the strain in the circumferential direction and the strain in the axial direction. So if I do a tensile test along the circumferential direction of my aorta, well, I will have positive strains in the circumferential direction, but due to the Poisson effect, I will have contraction in the other direction. So my test can be positioned here in this strain graph. And if I would do another test in the axial direction, I would be positioning here. But then if I look at where the artery or the aneurysm is at inside the body, well, this is the physiological domain. So basically, you can already appreciate from looking at this graph that we're not really doing the perfect test to really know how the tissue is going to feel inside the body. And there are many different kinds of in vitro tests that you could try to do. And here it really depends. You always have to try, depending on your application, whether it's cartilage or brain or cardiovascular or something else, try to find that test for which the loading conditions and the strain conditions are as similar as possible to how the tissue is being loaded inside the body. And of course, that's a trade-off between practical feasibility and biological relevance, because in this case, well, we don't get a wealth of data. We just have this small slab of tissue that we can use, and we try to use it for as much as possible because we want to use it for histological purposes and then for the mechanics. So we're always fighting over that little piece of tissue that comes from the patient. So basically for us, uniaxial tensile testing was the only possible alternative for getting at least a bit of information. What we could also do, what some groups have been doing, are bulge inflation tests. So there you actually take a flat membrane-like piece of your aneurysm or another piece of tissue, and then you inflate it, and then you could say, well, that at least in the central area of such a bulge inflation test, you would have equibiaxial tensile conditions, so you would hit the physiological domain in a better way. But the disadvantage is that you need quite a big portion of material to have, to not suffer too much from boundary effects. So, well, it's a trade-off that we need to make, and we are allowed to make it if we are aware of the fact that we're, again, making a modeling assumption, namely that our uniaxial tensile test does have a representative failure mode. Another question. We're doing in vitro tests. We're collecting the tissue from the patient and, well, usually freezing it directly, and then we thaw it, and then we do our mechanical tests. What does that do to our mechanical properties? Also that we need to analyze. And here, for example, we tested the effect of on the high stiffness modulus, so basically the tangent of your stress-stretch curve here. And we tested the effect of just having fresh tissues, so immediately testing them after collection or within 2-3 hours, or then doing a slow freezing procedure and then storing it just for 1 week, or slow freezing and storing it for 6 months, and then a fast freezing procedure where we freeze it, snap freeze it in isopentane. And you can see that, well, actually all of them are significantly different to our fresh control conditions, which means that we are definitely changing the mechanical properties of your tissue when you are preserving it and then using it for in vitro analysis. So that's another modeling assumption. We assume that preservation does not problematically affect our material properties. We have to be pragmatic about it because it's, at this point, the only way where we can really make reliable estimations of when the tissue is going to fail. So, are we doing the right test? Maybe, or it's the best possible test within the practical conditions that we have at hand. And then the second question is, are we doing the test right? And, well, here it's still a simple uniaxial tensile test, so even for the people who are not really into biomechanics, it's still easy to interpret. We can we can plot everything on a stress curve, and then we can see where the tissue fails, so where the ultimate first Biaxial stress is reached and where the ultimate stretch is reached. And of course, when we do that, we have a lot of measurement uncertainties because we measure the first Biaxial stress by taking the measured load, and dividing it by the undeformed surface area. So that means that we are susceptible to load cell inaccuracies, uncertainties. We are susceptible to mistakes and inaccuracies in our width and thickness measurement of our surface area. And also, even if we do digital image correlation or strain mapping to check how the tissue is elongating, this definitely is also susceptible to errors in the strain measurement. And then finally, well, the question is also, when exactly does the tissue fail? What do you call tissue failure? Is it really when the force drops down almost to zero? Or do you count micro cracks also as being problematic? So there's also a discussion there as which point you should take as your actual failure point. So, well, we felt like, okay, we already have quite some experience in doing these simple uniaxial tensile tests, and it's not such a difficult test, but maybe we can learn from others, and maybe others are doing the test better than we are. And also we noticed in the community that there was still quite some discussion on how to do mechanical testing in general. And that's why we created, also together with the VPH Institute and the Avicenna Alliance, we created the C4Bio initiative, where we brought different groups together in a community challenge to try and find consensus on how to characterize biological tissue. So this is, well, the initiative is really created in a broader sense, all kinds of characterization of biological tissue, but we decided to focus first on mechanical testing and to start simple with uniaxial tensile testing. But the idea, or let's say the problem, is that at this point, there are still no standards or best practices available on how to do biological tissue characterization. And the data that is out there is, well, it's not always very reliable. It's not very clear which methodologies were taken, and people seem to change methodologies between different publications. So we wanted to start simple. We thought as a warm-up, let's just have all interested participants join, where we all just do a simple set of uniaxial tensile tests. So what we did in our lab at KU Leuven, we went to collect 100 porcine aortas from the slaughterhouse, from the same age, same strain, same storage conditions. We prepared them into samples, so we had a couple of circumferentially oriented samples, a couple of axially oriented samples. We also sent along some synthetic material for comparison and to avoid biological variability. We sent those samples to all the participants around the world, and we asked them to bring back just this simple stress-stretch curve. So actually quite a lot of people were excited to join. It seems that everybody is suffering from this lack of standards, this lack of consensus. So we had quite a good turn-up of 25 participating groups. But the results were terribly disappointing. So we thought, okay, uniaxial tensile test should just be the warm-up and should set the bar for how we then do the tests that we really want to do, like biaxial tensile testing and other kinds of tests. But we had so much trouble just to interpret the data that came in. There was so much variability. Well, basically the variability was just plus minus 100%. So it was just almost impossible to report. So we thought, okay, maybe we were just a bit too open. And well, it was the idea. In this first round, let's just first have everybody test the way they were always testing, the way they prefer to do the test. But then we thought, okay, we really need to try and bring these things together. So we sat down with all the participants and we created a 16-page consensus protocol. We had a cutting tool so that everybody cut the samples in exactly the same way. We prescribed the shape of the sample. We prescribed the protocol with the preconditioning phase, and we were very clear on how to do marker tracking or digital image correlation. So we were very confident that this time we would get it right. And well, a bit of good news, let's say the surface area of the samples, the research group variability there was significantly reduced, but that's, well, I mean, if we wouldn't even have managed that when everybody got the same cutting tool, well, then we should have all just gone home. But what we really wanted to have a reduction in were these tangent moduli, and here there was simply no significant reduction in the tangent moduli between the different research groups. So everybody was actually just really disappointed. And actually, well, it's not always nice to bring bad news, but that's where we're at right now. So we are all very disappointed phase, and we really need to do something about this. So this is something that will be continued, and in the coming months, we will try to figure out really where the problem is coming from. And we have to try and figure this out, because basically if we cannot get it to work for a simple uniaxial tensile test, well, then what are we doing with all our more complicated mechanical tests? So to be continued and to be considered that there's not just biological variability, there's not just measurement uncertainty within a research group, there's a lot of measurement uncertainty between research groups. So just simply comparing data sets and comparing finite element models that use different data sets is very dangerous to do or should be done with care. So, well, that's a recap of all the kinds of variabilities and uncertainties for uniaxial tensile testing to get an idea of aortic tissue strength. It's quite a list. And then we have to still go to the final part of how to get our patient-specific material parameters, so the actual parameters that then go into the finite element model. There, the workflow is the same. We do a retrospective analysis. So again, patients that are already scheduled for surgery, we ask them to donate their tissue, we bring it to the lab, and we do biaxial tensile testing on it, and that we can put into a database. So obviously, again, it suffers from all the same problems of intra-patient variability and the fact that we only have a limited data set of material. And this is the same list as for uniaxial tensile testing. We don't have to really repeat all of it. I will just go through the specific elements that are worth to mention for biaxial testing, but it's obviously susceptible to all the same kind of errors. But looking at planar biaxial tensile testing, at least there we think that we're doing a better job than uniaxial tensile testing. We are hitting the physiological domain better than for uniaxial tensile testing. And what's good with planar biaxial testing is that you can play around a bit with the ratio, so you can pull a bit more in the one direction and in the other direction. So you could actually, by doing multiple rounds, you can try to span more of your physiological domain. But still, looking at how the tissue is being loaded inside the body versus how we are doing it in vitro, there are this bottom row could be far more representative for what's actually going on inside the body. And there, in an aneurysm or in the aorta, there might even be some torsion going on. So a kind of triaxial way of testing would be more reliable, but again, we have to make our trade-off of being pragmatic versus having reliable data. But maybe just as for completeness, well, if you would do an extension inflation test, there you really are loading the tissue according to, or a lot more according to how it's being loaded in the body. But the problem is we never get nice tubular samples to be able to do that without suffering from boundary condition effects. So we need to make this modeling assumption again that our biaxial tensile test is representative enough for our loading regime that we're going to put in our finite element model. Well, you're not all biomechanics crowd, so we don't have to go through all the details of how to do biaxial testing, but those who are interested, we have a nice YouTube video on how we feel that biaxial testing, tensile testing could be done. And there's a lot of aspects to discuss and a lot of places where things can go wrong in terms of dealing with boundary conditions, in terms of doing 2D digital image correlation, so having a one camera or two cameras to be able to do 3D digital image correlation, or other details like how to correct for the fact that you always preload your sample a bit. I don't think this is the right time and place to talk about all those details, but if you would be interested, here are the publications, and I think we can share these slides. That's everything related to, are we doing the test right, and are we doing the right test? Another question is, because now we're going to use these stress strain data that come from the planar biaxial test, we're going to use it for our finite element model. Are we doing proper data analysis? And therefore, we have to think about the constitutive model that we're going to use in our finite element simulation. And I always like to organize, there are so many different constitutive models that represent or try to represent the physical reality in terms of mechanical behavior of biological tissue. And I always like to organize them according to these three axes. So are they suitable for large deformation? Are they time dependent? And how biofidelic are they? So linear elastic models, which actually still many people use, are all the way at the 000 level of these constitutive models. They don't take any of that into account. Whereas, for example, if you would go for a neo-Hookean material model, you would at least already be suitable for large deformation. Or if you would have a Maxwell viscoelastic model, you would at least have some time dependency in your models. But there are many improvements that you can make. You could make some fiber reinforcement and go for the gastroognos Zapfel model. You could go for more elements in your Maxwell or in your viscoelastic system, or you could go for something poroelastic or biphasic elastic. And then obviously you can try to make the transection and try to combine these models in fiber reinforced poro-hyperelastic models, or you can go even further and add some swelling and some other chemomechanical effects into these models. So you can really go quite crazy in these constitutive models. And at some point you have to decide which one you're going to take. And once you've made that decision, you have made quite a strong modeling assumption that your constitutive model is appropriate is an appropriate representation of your actual material behavior. And there's a lot of research ongoing on model selection techniques to really try to find the best constitutive model for your specific data set. And there again, just like with the actual mechanical testing, it's a trade-off between complexity, because obviously the further you go along this biofidelity axis, the more material parameters you have, the more nonlinearities and the more computational difficulties you will have implementation-wise. So you need to make that trade-off. And once you make it, you need to get an impression on how big an effect that will have in your modeling assumptions. And once you've chosen your material model, you have to calibrate it. And there, obviously, you need to take your experimental data, which never looks as nice as this, but let's assume that this is your experimental data. Then you have chosen a certain constitutive model, and obviously, when you just choose random parameters for your model, there will be a gap there, and then you can do some kind of iterative process to find your correct constitutive model, and the parameters, no, you already chose your constitutive model, but to choose the parameters that best fit your experiment. And so that usually for mechanical testing that goes like this. So you perform your mechanical experiment, which means that you can measure some forces in different directions, and you can measure a deformation gradient using a camera. You can then, with that information, calculate experimental values for your stress. So stress is force divided by surface area. And on the other hand, you have your model, which in biomechanics we often represent using a strain energy density function. So with that strain energy density function and information about the deformation gradient, we can then calculate our second Piola-Kirchhoff stress, which we can then transform to the first Piola-Kirchhoff stress. And once we've done all the math correctly, we can minimize an objective function. So we can minimize the model stress and with respect to the experimental stress for each direction in which we did our test. So it could be 2 directions for planar biaxial, it could be 3 if we do triaxial testing, that depends. And we need to obviously update our material parameters until we've reached the minimum of our objective function. So the objective function in a 2D framework would look something like this. And we obviously want to find our global minimum, and to make it computationally feasible, it means that we also have to set some boundaries in our parameter space. So let's say this is our parameter space, and we know or we assume that we will never have parameters lower than this value, higher than that value. So we can use, for example, a gradient-based method, least squares, that you can find in any Python toolbox, to find our optimum parameter set. But there again, or well, just for your information, this is a very nice toolbox that was also developed in collaboration with Leuven that does a lot of, or helps you a lot to do proper optimization. But in any case, you will, if your experimental data is not perfect, I think we established that, which means that your model will never be a perfect representation of your experimental data, which means that you will never have reached a global minimum that's perfectly zero. And this discrepancy between 0 and the actual residual value of your optimization is what we call the calibration error. And this is, again, something that needs to propagate into the model. Another thing that might go wrong is that your constitutive model is not a polyconvex function, which means that if you use a gradient-based search method, you might get stuck in some local minima. And the problem there, or the way to solve that problem, is to do your fitting multiple times and make sure that you actually use multiple starting points so that you can then find the minimum of all the minima that you found, which, well, is something that you should do, but of course, the more starting points you take, again, the more computationally intensive everything becomes, so you're adding on to the total complexity of your system. So you always need to take into account that you might be stuck in some local minimum. And so then, well, once you've made all those decisions, you can do parameter fitting. In this case, for example, on the Gasser-Ogden-Holzapfel constitutive model is the one we used. And here you can see, for example, for all the patients that we tested, the distribution for a certain shear modulus parameter C1, and then we fitted a log normal distribution on that, and that's obviously another modeling assumption that we make, but we're still dealing with the fact that we are using a retrospective database. So this distribution function is not very specific to the patient that I want to analyze and for which I want to check whether he or she is at risk for aneurysm rupture. So we need to find ways to kind of narrow down this distribution for our prospective patient that we get in the clinic. For that, there are things that you can do. What we do, for example, is we take some other clinical parameters of the patient, in this case, the pulse wave velocity. So we look at the change in pressure in the patient versus the change in surface area of the aneurysm. And by having that information, we can narrow down the subspace in which, or we can narrow down the distribution function for our specific patient in terms of the different parameters, in this case of our gastroogmenal model. Maybe that's not entirely clear. If you would want to read more about that, there's a publication about that as well. So what we're simply trying to do is we have a large database that is spanning all the patients that we were able to collect in the database, but we try to make it specific by using some in vivo measurable data of our specific patient. Okay, so recap, again, a whole list of errors and variabilities and uncertainties that go into our model. And well, I have to say that when we were building up this list with when I was doing that with my PhD student, we were getting quite depressed, because if you put all of them together, well, you might end up with something that's just completely uninterpretable anymore. But well, scientists always have to be, well, they have to be realistic, but also a bit optimistic. So we really wanted to see what can still be done with that kind of data. So the bright side of this is that, well, let's say at least now we know that we are making mistakes, and we have an idea, and we have quantified many of these areas of uncertainty and assumptions. So that's one thing, and that's something, well, that we now did for this case of ascending thoracic aortic aneurysms, but it's a framework that can be used for any approach towards in silico modeling. So that's the first bright side, and the second thing, of course, is now that we have quantified them, and now that we have decided which probability distribution functions match with all these sources, there are methods to propagate this uncertainty through the model. And there are many researchers are working on smart ways to do that. And well, we're definitely not the experts there. We're the users. We use simple Python toolboxes for that. But basically, your input uncertainty gets sampled in some kind of smart way. In this case, for example, you could do smart sampling using Latin hypercube sampling, and then propagate that into either the direct computational model or some surrogate model, because your finite element model is usually quite expensive, so it's easier if you want to test all those variations to make some kind of surrogate model and then quantify what the distribution is of your output or your quantity of interest. So, well, there's a lot of development in that field. And we can't go into that right now, but there are libraries and also in Python free libraries available on how to do this kind of error propagation or uncertainty propagation. Because then once you've done that, you can also do sensitivity analysis, and you can try to figure out, of all these uncertain input parameters that we have in our system, which of them are actually the most important. So in the case for us to look at the delta moment-independent indices, so actually this means the higher this value, it means the larger the effect it has on your output value of interest, which in our case was the peak wall stress in the circumferential direction. And well, in here, not very surprisingly, you would say the wall thickness is the most critical parameter for us to really make sure that we try to get that as correctly as possible. So it gives you a bit of an idea of how to deal with that whole, swamp of uncertainties, and try to pick at least those ones out that are the most important, and tell your experimentalist colleague to focus on that one. And then fourthly, so once we have identified these uncertainties and we have a way to propagate them through the system, we can indeed calculate our probability of a certain peak wall stress and our probability of a certain wall strength for a specific patient. And basically, instead of having an absolute or deterministic failure risk, you can make a probabilistic failure risk, which is basically the area of overlap between those two curves. So, the more overlap, the more chances you have that you are at risk for a dissection or a rupture. And you can compare that between different patients if and only if you have analyzed those patients with the same methodology. Because, of course, if you do one patient with a very uncertain or very messy kind of biaxial testing and the other patient you do with more accurate biaxial testing, this overlap will be a result of measurement uncertainty and it will not be a result of your actual inherent patient uncertainty. So if you are consistent, it is possible to make relative comparisons between patients. So that's what we did for all the patients in our study. And we tried to, well, bring it back to the very beginning of the clinical question, where the cardiac surgeons tell us, well, this diameter criterion, we really think it's not a good idea. And so we plotted the probabilistic failure risk indices versus this systolic diameter in the patient. And yes, it's true. I mean, their intuition is correct. We found no correlation between diameter and this probabilistic rupture risk index. Maybe there is a better criterion. Maybe, I mean, the solution could be from now on, we always have to do this very tedious in silico simulation, which is good. It gives jobs to in silico analysts, which is good. But if we can make it easier, all the better. A better criterion might be, let's do segmentation on the diastolic phase of our patient scan and the systolic phase, take out the volumes, and then calculate what we call a distensibility coefficient. So the difference in volume between the two phases divided by the difference in pressure between the two phases, which is, well, actually already a used measure, but it was, up to now, it was only used in terms of diameters, so never in terms of volume. So we decided to create this volume-based distensibility coefficient. And we were very happy to see that when we then correlate this coefficient to our probabilistic failure risk, we did get a more convincing correlation. So, well, what that shows us is that in silico modeling can help, and it is a whole pathway, a complex pathway, but that can help to maybe bring you back to something more simple. In this case, a relatively simple index, this distensibility coefficient. We still don't have enough patients yet, and we need to expand our database and do more in silico modeling, but in silico modeling can now be used as a tool to prove that another more simple metric, which is less susceptible to this uncertainty, can be used in the future for clinical predictions. So as a take-home message, well, in silico scientists like you should be conscious of all the sources of uncertainty and variability in your input parameters. So I hope that I brought that message across. And you should go and tell your experimentalist friends to continue to work together to try to minimize measurement uncertainty. And thanks to this uncertainty propagation and sensitivity analysis, you can tell them which parameters to focus on first. And then, well, to bring a positive note, we know that the uncertainty is very high in our case, but even when it is high, in silico modeling can be used, so we shouldn't despair, but we need to be consistent in the quality of our input parameters, and we need to, as much as possible, work with relative comparators so that we can, well, kind of filter out the measurement uncertainties in a way. So with that, I'd like to thank you for your attention and also thank my group for working on this, and especially my PhD student Klaas van der Linde, who helped me a lot in preparing this data set. So, and all the C4 Bio participants, of course, as well, and the cardiac surgeons in our group. So thank you, And if there are any questions, I'm happy to answer them.
Thank you for this interesting presentation. If anyone has any questions. Oh, okay.
Thank you. That was super interesting. So I'm always very much interested in uncertainty modeling. I come more from an image analysis type of community, but the issues and the methodologies are quite common. We always have a bit of an issue of what to do with it in the end, right? Because it's quite an effort to try to model everything, to find the right modeling assumptions, to see the methods to propagate. But then you collaborate with final end users, and they say, okay, but what are you going to give me as an output? Are you going to give me some error bars? Are you going to give me some distributions, a probability index? So I don't know if you have any guidelines or any experiences that you can share.
Yeah, well, only experience, not guidelines. Indeed, the surgeons want something interpretable, preferably just one number. so that's why I also add these. It doesn't sound good. These reporting errors to the total scheme. Make a really complex model. Microphone. Hello. Should I just maybe take another one? I'll go stand here. Hello. Oh. Yes, something as simple as possible, but still, well, somebody needs to be aware of everything that's behind it. But that's why here we were quite happy to see this nice correlation between our probabilistic rupture risk index, which really has all this propagation of all of the uncertainty and the variability. We were happy to see that it correlated with something far more simple, like this sensibility coefficient. So I think if you can use it in such a way, then you get lucky. But of course, it's not always that easy. So I don't have an answer.
Thank you. Really nice overview.
Thank you.
And obviously, the microphones seem to be a bit tricky today. And obviously, I like the last part. So I think that's what we need to do as modelers, indeed, give input into clinicians, find new parameters or support parameters. That I like very much. But let me first come back to your experience with this uniaxial testing and the variability.
Traumatic experience.
But are you surprised?
Yes. Yes, we were surprised.
Then maybe you haven't worked enough in clinical practice, because this is what you always see when you ask this.
Yes, but in this case, we sent the same type of aorta to all groups of which we know are experts in biomechanical testing. And uniaxial tensile testing is like the basics of the basics. So we thought, well, we knew there was going to be variability, but we really didn't expect this much, especially after the consensus protocol.
Did you do the same experiment, but then just do the measurements in your own lab, but all the rest the same?
Well, we also did the experiments in our lab, so we have our own intra-research group variability.
Yeah, but following the same protocol? If you do your intra-research, so you do exactly the same, but instead of sending out the samples, you just process them locally. And maybe have them processed by a few people that do it.
Yes, we did do that as well. So we did do a post-processing of the same data set by multiple groups, and that's not the reason.
No. I mean the measurement itself. So my question is a little bit, is the variability into the measurement, or is the variability into the samples?
We also sent synthetic samples, and the variability of the synthetic samples was same order of magnitude as the biological ones. So it's really at the beginning. It's at the front end of the problem. And actually now we're still reanalyzing everything that was submitted by the participants, and we simply noticed that even though we all think we applied a certain protocol, many of us didn't really apply that protocol in the end. So it's really a matter of, some essential things that are still missing in how we implement our tests, and we're a bit too confident, all of us are a bit too confident that it's all going okay, and
Yeah. And the other thing is, like, since aorta is so anisotropic, so your longitudinal versus circumferential, it's always tricky, of course, is like in which directions. Yeah. Did you ever try to do this under imaging, like, for example, phase contrast X-ray imaging, to really combine it with the structure?
Well, not in this initiative yet, because, on here we wanted to have as many people on board as possible, which means that you can't put too many restrictions on the kind of equipment that should be available. But we are working on doing in situ tensile testing using contrast-enhanced CT imaging. So there we would have 4D CT information during a uniaxial tensile test. Problem there is, we see the elastin but not the collagen. But there are groups who are doing that with second harmonic generation as well. So yes, it's being done more and more. But then, there's the multi-scale problem of how to link your tissue scale material models to what's really going on with the fibers at the micro scale. And that's another area of research again.
Mm. And on the other hand, maybe leave some other people first.
I was just going to ask your probabilistic failure model. Do you have any sense of how that correlates with like real failures from real data? Because if it's retrospective, do you have like how many of those actually resulted in failures?
Yeah, that's a bit the problem with our. It's the selection bias in the sense that we don't have information of people who failed, because we only have information of people who are scheduled for surgery, and obviously they survived until they entered the surgical theater, so they didn't rupture yet. And to get cases of people who have a ruptured aneurysm and that are not yet in follow-up in the clinic, that's ethically also very difficult, because this is not always autopsied. Sometimes it's just an assumption of the doctor who identifies the cause of death. But it's not that unless these people have in advance decided to donate their body to science, we would never be able to get a hold of those samples. That's the difficulty. That's the bias that we have.
The other question I had was when you're sort of fitting these model parameters, do you have a sense of when you have sort of taken enough measurements to kind of uniquely define your parameter space? Because your parameter space can be quite large, right? Mm-hmm. So with things like the pulse wave velocity correction thing like that, mm-hmm. Do you have a sense of how much data you need in order to have a sort of unique optimization minimum?
Well, I think you can always find some unique or the global minimum. The question is how off is it from reality? I think, somehow it's a mixed question. Do you mean how do you narrow it down for a certain patient? Or how do you make sure that you have your global minimum? I'm not sure where you're getting at.
I think with sometimes I'm not sure what sort of parameter space you're working with, but if you have like a very large parameter space,
there are physical limits. For some of the values, there really just are physical limits, like the angle of the fibers or the stiffness. There are some physical limits that you would know that your collagen fibers never have a stiffness higher than this or that amount of megapascal. But so I'm not sure what you're getting at.
Okay, no problem. Maybe I'll ask later.
Yeah.
Other questions?
Right, that was an interesting talk. I didn't understand the risk slides at all. Do you have a paper? I've got your list of papers here. Do you have a paper you can direct me to so I can read up more about that?
It's under review.
Okay.
So, yeah. But there is a paper, I did put a link of the group of Stan Polzer from Czech Republic, and he has done something similar for abdominal aneurysms, where they do define a probabilistic risk, but there it's related really just to inter-patient variability, not related to measurement uncertainty. So, but it's a similar approach.
Yeah, I just have another quick question, kind of following on from the question about the pulse wave velocity in your material properties.
Yeah.
Did you observe any other patterns amongst the population of material properties that clinical parameters that you could use to say if you only had patient age available, would that be appropriate?
Yeah, and that's indeed something else that we would try to do a regression analysis and see if you combine age with gender and cholesterol or all these things, and there are correlations indeed. But the data set is still rather limited, so you just need a lot more data to be able to confidently do that regression analysis. But definitely we do see these correlations.
Okay, perfect. Yeah. Thank you.
Maybe one more quick question is when you look in clinical practice, for example, failure and rupture and a lot of these kind of traumatic events mostly happen in a stress or a dynamic situation. Mm-hmm. While although you take intra-variability of stresses or pressures or whatever, I rarely see a kind of exercise or stress kind of simulations where you really go from, a sudden increase in pressure, for example. Mm. Why not that? Why in reality you know that this is really relevant?
The question is it the dynamic effect that then would speed up or higher the chance of rupture, or is it just the high pressure? And up to now, these models are indeed hyperelastic, so there's no time dependency in them, no rate effect. I think up to now, the assumption is still that the time scale of this pressure increase is low enough to be able to model that in a quasi-static manner. Mm. But it's an assumption.
The end pressure is often much, much higher, no, than what is simulated in a stress situation.
Well, those we do try to take into account. So to really take but it's still quasi-static, but it is the maximum pressure that can occur in a patient.
Thank you.
Yeah.
We don't have more time for questions, so thank you again, Dr. Nele Famaey.